For the continuous time signal, I define two signals. X1 is a sine wave, sine t, and X2 is a cosine wave, cos t. Both signals are generated over a time vector from 0 to 10 seconds with 1000 points for smooth plotting. Now for the addition part, we add the sine and cosine signal together. We are summing their value at every instant of time. This creates a new wave where sometimes the amplitude add up constructive interference and sometimes they cancel each other, destructive interference. Constructive interference happens when both signals are positive or both are negative. The amplitude add and the wave goes high. Destructive interference happens when one signal is positive and the other signal is negative. They cancel out and the resulting amplitude is lower. That's why the result wave goes up and down irregularly, because the sine and cosine wave are not always in phase with each other. Instead of adding, we multiply the sine and cosine value point by point. When both signals have the same sign, the result is positive. When the one is positive and the other is negative, the result is negative. When either signal is close to zero, the result is also close to zero. This multiplication creates a modulate wave pattern that looks more compressed and faster. In the case of shifting a signal by 1 second to the right simulate a delay. If you observe the graph, the peaks and valleys occur later than they did originally. Mathematically, shifting replaces every t with t minus t, where t is delay. Here the sine wave is shifted by multiplying the time variable by 2. Now I will explain the result of my discrete time signal operation using octave. First, let's look at addition. In the code, we create two signals where a sine wave sine 0.2 pi n and a cosine wave cos 0.2 pi n. Then we add them together point by point. When we add sine and cosine, sometimes both are positive, which make the result even large. Other time one is positive and one is negative, so they cancel each other a little. And when both are negative, they add up in the negative direction. This is why the graph goes up and down smoothly. It looks like a wider wave because of the way sine and cosine interact over time. Next is multiplication. Here we multiply the sine wave and cosine wave sample by sample. In mathematics, when you multiply sine and cosine, it becomes a sine wave with double the frequency and half the amplitude. This is because of the identity sine A cos A equals to 1 over 2 sine 2A. So when we look at the graph, we can see that it oscillates faster. It crosses zero more often. And the wave height is smaller compared to the original addition result. This is why the multiplication graph looks tighter and smaller. Let's talk about shifting. In the coding, we shift the sine wave by 3 units to the right using n-3. Shifting means we delay the signal. The shape of the sine wave doesn't change at all. It's exactly the same wave, but it starts a little later. In the graph, we can see the first few samples are now 0 and the sine wave begins only after 3 time steps. So in summary, for continuous time signal, for addition, addition combines two signals changing their shape and energy over time. For multiplication, it modifies amplitude and can introduce oscillation or rapid variation. For shifting, it moves the signal along the time axis, delaying or advancing it. Conclusion for discrete time signal, for addition, it combines two signals affecting their shape and energy at each time point. For multiplication, It alters oscillation speed and amplitude, modulating the signal frequency and intensity. For shifting, it delays the signal in time without changing its shape.
I would like to present the synthesis and conversion of three time-domain signal to the frequency domain using the fast Fourier transform or FFT. The main objective of this equation is to show how different time domain signal to a sinusoidal wave, a square wave, and a triangle wave can be analyzed in the frequency domain using a FFT function. First, let's look at the three signals we have selected. Signal 1 is a 50 Hz sinusoidal wave defined as x1 equal to 2 pi multiple 50 multiple t. And signal 2 is a 25 Hz square wave defined as x2 square 2 pi multiple 25 multiple t. And signal 3 is a 70 Hz triangle wave defined as x3 triangle 2 pi multiple 75 multiple t 0.5. Now, I would like to show you the coding part of this project. First, I define the sampling parameter, such as the sampling frequency, the time vector, and the length of the signal. These parameters are important to accurately capture the signal in the time domain. Next, I create the three different signals, a 50 Hz sinusoidal wave, a 25 Hz square wave, and a 75 Hz triangle wave. Each of them is generated using the standard mathematical function. Then I applied to the fast Fourier transform using the FFT function. This function converts the time domain signal into its frequency domain representative. Finally, I extract the magnitude spectrum and plot the result. The plot shows the amplitude of each frequency component in the signal. Overall, this could help us to move from time domain analysis to frequency domain analysis efficiently. Each of these signals has a different characteristic in the time domain. Next, we use the fast Fourier transform or FFT to convert the signal into the frequency domain. FFT allows us to observe the frequency component in each signal. After applying FFT, we obtain the following result. For the sinusoidal wave, we observe a single sharp peak at 55 Hz. For the square wave, we see multiple peaks, the fundamental 8, 25 Hz, and its odd harmonic, such as 75 Hz, 125 Hz, and so on. For the triangle wave, we also see multiple harmonic, but the higher harmonic decrease much faster compared to the square wave. This shows how different waves. In conclusion, by using fast Fourier transform, we are able to analyze and understand the hidden frequency component in time domain signal. Different types of signal, even if they seem similar, have unique frequency signature. This analysis is very important in areas such as communication, system and audio processing, and signal analysis. That's from me. Thank you.